Welcome to The Outsender. This is the English version of the previous one I did in Swedish regarding this antenna. And in this bag I have a 9-to-1 transformer and a piece of antenna wire, and well, that's your regular random wire, long wire type of setup. But with this antenna you have the option to add a 500 ohm terminating resistor somewhere along that antenna wire. And I will go into the details of the measurements shortly. But this antenna has dual purposes, or dual use rather. So it can either be used as your normal random wire, long wire type of antenna, where you have the 9-to-1 impedance transformer somewhere where you want to operate, close by anyway, and you feed it with a piece of coax to your antenna tuning unit, your antenna coupler or impedance matching unit, whatever you want to call it. And then you just put up the wire as a sloper usually, or you can put it up horizontally about 2 meters above ground or something for typical near vertical incident skywave work. But you need an antenna tuning unit. So the application of this antenna is mainly as a military type of antenna, or maybe a civil defense type of portable emergency type of antenna. But it has two purposes with the terminating resistor. That makes it a wideband end-fed antenna. So with that I mean that it has close to a 50 ohm match on a pretty wide range of the HF spectrum. And the design goal of this antenna, which I'm pretty satisfied with, since I could model this one in software in NEC 2, and I got pretty much the same result, or close to the same result, with a realized product here. So that's why I consider this one to be, you know, a more finalized version. So it may actually have some improvements regarding measurements and design and whatever, but at least it works as intended. So the other application would be use this one as a wideband antenna for matching it to a 50 ohm rig directly without an antenna tuning unit. And the main application is automatic link establishment, ALE, with older radios possibly then, who doesn't have a fast antenna coupler built into them. And well, those type of antennas have been used for this purpose for a long time, and it doesn't have to be the automatic mode, the ALE mode. It could be manual, that you just change frequencies to those you're assigned to find whatever works best, or you have to change band completely during nighttime, or your frequencies shift you know, regarding your assigned channels and whatever. So it mainly has a military purpose or civil defense purpose, whatever. And the design goal is also as a portable antenna, that you can pretty much put it up very easily everywhere in all types of terrain, and you can be more maneuverable, so you can put up the antenna, you can break it pretty fast, and that's the whole purpose of this one, and it doesn't weigh that much depending on which type of antenna wire you use. However, so we have the impedance matching unit here, and that's where you sit and feed the rig. And then there is 26 meters of antenna wire, and after 26 meters there's the option to add the 500 ohm terminating resistor, and after that there is 15 meters of trailing antenna wire. So 26 meters, 500 ohm terminating resistor, 15 meters trailing antenna wire. And the only grounding for this one is at the transformer end, where you have a counterpoise going into a pretty small grounding rod, a very short grounding rod, but it actually works and makes a big difference of the standing wave ratio. So the 2-to-1 standing wave ratio bandwidth of this antenna is somewhere from 1.6 megahertz thereabout, or even a bit lower actually, and up to maybe 6.8 megahertz or something, or maybe even 7 megahertz, depending on the terrain and ground and everything. The difference between this antenna, a 91 end-fed random wire, long wire type of antenna, with or without the terminating resistor, And the previous one I demonstrated the delta loop with a 1000 ohm terminating resistor and a 16:1 impedance transformer, and the configuration was like a delta loop, and it was a closed circuit. This is not a closed circuit. So the previous one, the delta loop type of antenna, which is Bonnie Crystal's design, by the way, and that appears to, well, it's much wider in its frequency range, and it doesn't appear to be that sensitive to different type of grounds. Maybe it's sensitive to how you elevate it or not, or how far away you separate the transformer and the resistor. That would be sensitive. But grounding doesn't seem to be, that type of antenna doesn't seem to be affected that badly by different type of grounds. However, a 91 random wire long wire type of antenna is always sensitive to grounding, and you may already know that. So in this case, that's also true for the bandwidth of this antenna, and that's why that you will probably see a different result. And you cannot say that the bandwidth is exact up to 7 megahertz, but at least it will cover the usable near vertical incidence skywave spectrum for northern hemisphere, basically, where I'm at. So that's what this type of antenna is designed for, to be able to use near vertical incidence skywave where I'm at. So it may not be usable in the equator. You would probably have to maybe shorten it and use the same ratio or whatever. We'll have to model that for that purpose, but it will work for the environment I'm in. So well, far up north, the FOF2, the frequency of the ordinary mode of the F2 layer, the highest refracted frequency, it usually goes even below 1.6 megahertz during winter, the darkest hour of the nights. So that's a problem up north, and then you would have to use very long antennas, and you obviously also need a radio, that a transceiver that actually can transmit below that. So this antenna is for that purpose and further south then. So we have some colorful lines here. These would obviously not be used in a military setting, but I used these when I tested this one in a park, so that people didn't trip over the lines and they could see it in case there was someone close by. But those will be replaced with green, OD green, or black lines instead, obviously. And I have a throw bag here. These are very convenient, and if you get this one in your head, it doesn't hurt you that much, and well, at least you don't become injured seriously with this type of bag. Here we have some counterports. This is just 9 meters. It's the only counterports that is included with this antenna, and here's the ground rod, the very small ground rod, but it made a huge difference. We have some coax, pretty short one, I think it's like 5 meters. And here we have the 91 transformer and the 500 ohm terminating resistor, and that's just about it what this antenna includes. So the 91 transformer is made up of a FT140-43, the material is 43, and it's wound with magnet wire, 5 trifilar windings. That made it a pretty good match of on the HF spectrum, at least, even from the low end, like the upper part of MF and all of HF. And one important thing to note about this also is that the windings are a bit, they are slightly separate from each other, even if this is magnet wire, it's not tight. And the reason for that is that I discovered that if you match the characteristic impedance, and the characteristic impedance of this one is 450 ohms, if you get somewhere close at least, you don't have a standing wave ratio loss or mismatch in the transmission line, since this is a transmission line transformer. So then you would also have a characteristic impedance in that one. So it's separated a little bit, and that made a huge difference in the the transformation ratio of this one. And that's also one reason why I could model the software to match this whole setup and to be able to match it in reality, like in this case then. So it has, antenna wire is 41 meters, as I said, and it's divided into one length that is 26 meters, and then there is another isolator in the middle here, as you can see, and you have these two here that either you connect them together, and what you would use is to just use this this type of you would use this one also, and you would connect it like that, and then it will be shorted, and then you can use it as a normal random wire or long wire type of antenna, or you can just put this one in series, obviously, like that, and then you have 500 ohms into the circuit in series, and that will make it you know, the wideband property of this antenna. That's how that is supposed to work. And then it has 15 meters going further to a tree then. So that's it. And yeah, well, the grounding thing, I have this grounding lug there, whatever you call it, and you have this wire here. It's 9 meters, and this one makes a huge difference actually of the standing wave ratio and the match. So even if this is a pretty small grounding rod, it actually works pretty well in different terrain also. So it made a huge difference compared to not using a ground rod, just using the counterpoise. This one added some a better match. So let's put this one up then, and I'm just going to elevate it 2 meters above ground for your typical near vertical incident skywave work, and I will measure it with an antenna analyzer. Now the antenna is elevated about 2 meters above ground, and here's the transformer again with the coax attached and the counterpoise going to the ground rod somewhere over there. And well, from here then it's elevated about 2 meters above ground. It's pretty tight, so it's actually horizontal to the terminating resistor, which is 26 meters in that direction, and after the terminating resistor there's 15 meters of wire leading, which is attached to a tree, a small spruce. So I hope that doesn't bend that much, because it's pretty tight now. So that's one reason I wanted to use this heavier gauge copper wire, and I will probably switch to something with greater tensile strength, probably something with a steel core, you know, copper steel mix type of wire for this application, so that you can really tighten it really well then to get it as horizontal as possible. So well, now it's time to measure this one. Does it perform as it did in the software modeling? That's the question. So here we can see that the bandwidth is from the 160 meter band. It's actually 2.0 in standing wave ratio at 1.755. and at 13 kilohertz it's 1.88, and then the upper end of this near vertical incidence skywave region or range of this antenna is to 6058 kilohertz. So it doesn't go to the 40 meter band in this installation, and then if you go to the 40 meter band you have a standing wave ratio of 2.4 basically. So that's not very good, but anyway, it meets the design goal, so that's the most important part here. It has a 2-to-1 wide range for the frequency range of choice here for the near vertical incidence skywave part of those frequencies. So that's okay, and you can also use it for, as you can see here, at the 20 meter band it has a standing wave ratio of 1.06. So yeah, you can use it there too, and you can probably use it higher also, but it has a big bump here where it goes even up to 3 in standing wave ratio. So that's not, it's a compromised antenna for this purpose, but at least it's pretty efficient for what it is, and that's the design goal. That's it for this episode of The Outsender, and I hope you enjoyed this one. I'll probably continue and make more of these type of antenna experiments in the near future, or in the future anyway. And well, I will probably experiment with different ratios, and perhaps try to find something that is shorter but still works on the intended frequency span. This is still, it's a 41 meter antenna, and well, it's pretty easy to erect anyway, to put up as a portable antenna, and that's the main purpose of it. You don't have to detach or attach all of the gear on it. You don't have to detach the terminating resistor, for instance. It can already be attached, and same thing with the transformer, and you can just bunch it up in a backpack or something, or in a different kind of bag or something, and then you could pretty easily just put it up and break it and move along. And that's the main purpose of this antenna, for a maneuverable unit like a patrol or something that for some reason wants to use HF, because that's probably the question I will get now then. Why not use VHF or UHF when you're maneuverable? You can communicate with everyone all the time, and yeah, that could be a problem in an electronically contested environment for this patrol in question and for this maneuverable unit. So the maneuverable unit wants to communicate, but does not want to be found, does not want to be geolocated. And VHF and UHF is pretty easy to geolocate, because you usually always receive the direct wave or the ground wave, or you could receive a multipath wave obviously, but usually when you have the stronger signal there, it's a direct wave, and then you can geolocate that position pretty exact. And with HF and near vertical incidence skywave in particular, it's very difficult to geolocate something precisely. So that's one purpose of this type of antenna, and why I designed it for that purpose also. So you would want to counter a signal reconnaissance element of a potential opponent. That's what you want to do with this, with using HF in a small maneuverable unit in the forest basically. And then you want to have an antenna that you can put up and break pretty easily and quickly and move along. So that's the design goal of using an end-fed antenna. It's usually easier to put up than some of the other antennas. But however, if you want a really broadband antenna, then I recommend the one in the previous episode, the Terminated delta loop antenna. It's not that difficult to put up anyway, so that works also. It's definitely easier to carry around, and that type of, and install it also than a terminated folded dipole with the separators that you have to use with that one. It becomes pretty bulky, and and it takes a while to put up those type of antennas. So wire antennas are always a bit easier anyway, I find, and that's definitely true with this type of antenna. So yeah, the ratio of this antenna is then 26 meter antenna wire, terminating resistor, followed by 15 meters of tail antenna wire. And the grounding is only at the transformer, as you've seen, so there's no grounding at the other end of the antenna wire. It's just attached to a tree, and the ratio would be 15 divided by 26, and that could possibly be a ratio that would work to shorten this antenna for perhaps more southern near vertical incidence skywave work. Like in the equator you would use higher frequencies, and then this antenna, as you see, it doesn't cover the 40 meter band, so up about 7 or 8 or 9 megahertz you would probably end up being able to use near the equator. Then you cannot use this antenna, so you would probably be able to shorten it with the same ratio, but I have to experiment more with that and perhaps model that a bit more to find out some other type of compromise for this type of antenna. Yeah, well, that's it, this episode, and if you like it, then please consider giving this video a thumbs up, and consider subscribing and also visiting my Patreon page at www.patreon.com/outsander, and consider becoming a patron. I really appreciate that and motivates me a lot to continue making this type of material. And you also get to join the Discord server if you're a patron, and that's where I have most of the conversations with the viewers who are patrons, obviously. And it's not in the YouTube comment section, so if you want to do more in-depth discussion, then the Discord server is my choice there, obviously. And you pay for it also, so that would make sense that I'm more active there than in the comment section. Well, that's it, and thank you for watching, and as I always say, 73, end of message, out.